Yes, it is. All right, so it's my great pleasure to welcome our first Institute lecture. And one of the ways that we are changing also things this year is we wanted to associate the center and all our many members, there's 87 of them from 14 different institutions in Quebec. Each was very kind to agree to be the opening Institute lecture this week. We had, as Farah mentioned, Amanda will be speaking on Friday, and then next week for week 2, we'll have Marcello Vitali Rossadi on Monday, and then Béatrice Joyeux-Prunel from the University of Geneva on Friday. I'm saying that not to encourage you to change your plane ticket at this stage, it's too late, but we'll be recording the lectures and make them available on the DHSI website later on. So each is the Canada Research Chair in Music Information Retrieval and a professor in the music technology area of the Department of Music Research at the Schulich School of Music at McGill University, just down the mountain. He holds bachelor degrees in mathematics and music, percussion, and from the University of Alberta, master's degree in music theory and a PhD in music technology from McGill University. From 1993 to 2002, he served as a faculty member in the computer music department at the Peabody's Conservatory of Music at Johns Hopkins University, and since his appointment at McGill in 2002, he has led the Distributed Digital Music Archives and Libraries Laboratory with a primary research focus on optical music recognition. For over 2 decades, he was a member of Montreal's traditional Japanese drumming group, Arashi Daiko, touring with them across North America and Europe, and it's our great pleasure to welcome him this morning. Thanks again, Ed.
Michael, for the introduction. I also want to thank Ray for doing all this. Right? So I want to talk about laziness. So because I'm so lazy, I'm just going to stop and not do anything for the next 60 minutes. So there is a disclaimer. Whoa. It's not happening. Okay, here we go. So I want to disclaim that some of these large language models have been used for the record. So what is laziness? So laziness is not the absence of work, but the art of avoiding unnecessary work, right? So laziness can be characterized by as the inclination to issues here. Technology, right? To avoid unnecessary effort, to optimize action, and to do only what is needed when it's needed. I think you understand what I'm talking about. So what are the virtues of laziness? Minimum effort, maximum outcome. Why do more than necessary? Laziness encourages elegant solutions, avoids overcomplication, doesn't waste time or energy. There's a strategic delay. Wait until time is right. We make excuses all the time, right? Postpone action until enough information is available. Avoid premature decisions, right? And foster adaptability. Questioning unnecessary labor. Does this really need doing? Recognize this diminishing returns. Sometimes we do too much work than necessary, and favors purpose over productivity, or just doing it, spinning your wheels. Okay, so I've been thinking laziness as design principle for a long time, because if the human laziness can lead to clarity, adaptability, and efficiency, what happens when we build machines that are lazy too? So that's what we're going to talk about today. So plan for this talk, I'll talk about lazy learning, which is a fairly common term in computing science, and lazy pedagogy. I'll talk mainly about, as a case study, our SIMSA project, which basically is about optical music recognition, and lazy searching. I put it in quotes because it's not a very common term. I like to think that I invented it, and also lazy storage. And for that, I use another project called Link Music Project, and I'll talk about that. And this is all about music database integration. Okay, so let me talk about OMR for a while. So OMR is a process of converting images of music scores into a symbolic computer representation, such as MIDI, music XML, or MEI. So we have an image of a score, and we convert that into a computer readable format. Typically, it could be XML. Some of you know what that is already, and this process is called OMR. It's sort of like OCR, but it's a little more complicated. So you start with digitized score, and you do some image pre-processing. We'll talk about this later. Then we do music symbol recognition. Then we do music notation reconstruction, because we take things apart on music and then we put it back together. So in each of these main steps, we have different things like binarization, noise removal, structural analysis, image segmentation. Then we have staves, processing staves are those typically 5-line parallel lines that you put the notes on top of. And symbol segmentation, symbol classification, symbol combination, semantic assignment. It's at this point we know what the pitches are or rhythm values are, and we put everything back together, and you get the output. Okay, so why is OMR important? Who cares? Well, it's good for automatic playback. Once it's in the computer, you can play it back. You can rearrange it easier. You can do things like transposition. If you can't sing this piece of song because it's too high, you can lower it. You want to make the change in modes, major to minors, and we can do symbolic music analysis. That's what music theorists do. You can also do searching, data binding, distant reading. Reprints. Publisher would like to take an old published non-digital edition and make it digital. Braille, for people who can't see music, and score following. Score following is where the machine will turn the page for you, or you can have a little bouncing balls so that you can pretend that you're following music. Okay, so a brief history of music, of optical music recognition. So the first PhD dissertation on OMR is 1966, 60 years ago at MIT. Here is the first published digital scan of music in 1970. This was it. This is all it's going to fit in the memory. Don't forget, in the 70s, we probably had 1,000th of what you have in your pocket on your phone, right? It's probably like 100K at most. But that's the one I found is the original. Okay, so then in 1984 was the first robot with OMR capabilities. So you can go see this thing. It still exists in Tsukuba University. There's a museum, and I've seen it a couple of times. I can go say hello. And it has a head. So you put music here, and it has a camera, and it's supposed to read and play. And actually, it's supposed to accompany a human singer. I haven't actually seen that, but it's very cool, especially that it was over 40 years ago. Recently, thanks to YouTube, I found a video from 1985. Oh, I forgot to get audio. Hopefully you will have sound here. Just make sure this is not going to blast everybody. Maybe volume. Try that. Not happening. Should have checked. Okay, so you'll hear it out from here.
楽譜を読み取って演奏するロボット。
this is 1985. So this was probably created by 100 university profs and students from, it's called a WABOT because it was done at Waseda University in Tokyo. All right, so then skip a few more years. In 2001, we created a software called Gamera. It's a framework for creation of structured document recognition system designed for domain experts, grad students, image processing tools. It has filters, binarization, etc., document segmentation analysis, symbol segmentation, and classification. And it was made portable, extensible, simple, open source with a GUI, graphic user interface, and batch processing. So batch means you can do many things over and over. Same thing. So that was important because we wanted to process number of pages, a book, a music book, score book. So Gamera does stand for something. I never remember it. Generalized algorithm and methods for enhancement and restoration of archives. However, many of you may know kaiju, Japanese monster movies. So it is a turtle. It was exposed to some radiation and got big. And there's a connection here, right? You know the story about the turtle and the hare, right? Kame, so kame is Japanese for turtle, and they're sort of slow and lazy. Anyways, so after that was 2001, then thanks to many reviewers in this room, I've got this project going called SIMSA, Single Interface for Music Score Searching Analysis. So think Google Scores, okay? Similar to Google Books, minus Google, but with music, not text. So obviously it'll use optical music recognition to enable full text search, sophisticated music analysis and query, access to digitized scores worldwide from a single website, right? We're not quite there yet, but we're very close. It was a 13-year project. It ended about a year ago, officially. We're still going. So the big picture or the big vision was to create global digital music library. So SIMSA, so the core is this OMR technology. We have had many digitized scores already. It's still growing, so we can use those. We also have books digitized, right? All of you know. And they're actually music inside books. And these were not ever cataloged. So we can rediscover, so there's few pages within the book, like The Hobbit has some music in it. We have great partners, large libraries with lots of music collections. We had decent metadata. It turned out it wasn't enough, but it was good enough to start. We had already had some tools. So we thought we'd build it, people would come and use it. Okay, so we concentrate on early music notation systems, mainly because no commercial software people will ever touch it because there's not just enough market for this, right? So these what they look like. This is from like 9th to 16th century. Yeah, they haven't really figured out or standardized how to notate music. I like this one, the birds on the telephone wires. Right, so this is what we were dealing with. So it was really necessary that we have an adaptive system so that we can teach each of these different symbols to the machines so we can OMR them. Note that this one doesn't even have staff lines. And we actually don't know what the pitches are. So the first project we did in 2011 was called the Liber Usualis project. It's one of those books that has lots of Gregorian chant. It's a square notation. It's actually began to publish late 19th century and used throughout sort of the first half of the 20th century. So it has 2,000 pages of Latin text. Actually, it has other. This one particular has English, and what's called the square notation. Okay, so that's what we did. It was already digitized, and we wanted to do the whole thing. And it took a while, a couple of years, but we have this website where you can search by pitch or text through this entire book. Now, it's still up. Apparently, people or musicologists or teachers like to use it in their classes, so it's still going after what now, 14 years. Okay, then we discovered something really, really cool, and sure people really like this, and you'll know why, because there was a manuscript in Canada, right? It's like St. Mary's University. It was done in 1554. It was copied. These are all these things are huge, right? They're shared by monks or nuns. This was from the Cistercian Abbey of Sauzen in Namur, Belgium. We went there. We brought it back actually for exhibition, and it actually was a nunnery. There are nuns here, and beneath it, you can't see it here, but there are their names actually. Sister Mary, Sister. It's really, really nice. It's a beautiful manuscript. It was brought to Halifax in the 1840s by a certain Archbishop William Walsh. And so we wanted to digitize that. That was our next big project. Now, Andrew Hankinson, who worked on the original Libre as well, has such a hard time doing the work because there's so many steps. It was a pain. So he said, was a PhD student, and he said, well, I'm going to make this much easier. So his project called Rodin, can't read it, can't move this thing out. Anyways, it's called Rodin Remote Online Document Analysis Network. Remember Gamera? So if the Gamera goes to the cloud and starts flying, it's called Rodin. All right, so it's a workflow management system for large-scale optical music recognition process, large scale. File management, cropping, head rotation, noise removal, binarization, sub-register segmentation, symbol recognition, corrections, and build indices for searching. Okay, this is sort of original screenshot. It sort of looks like now it's all graphic so people can build their own workflow system. Then in 2016, we had a huge breakthrough in OMR pre-processing. So at the document analysis stage, we started doing what's called the pixel level classification so that we can separate background from text and staff lines and musical symbols. And this one uses convolutional neural network, and it was done by another PhD who was a visiting PhD student and came back as a postdoc from University of Alicante. He's still there. We call this the Calvo's method, and it's quite amazing. Let me go through, just as a review, what are the process of doing OMR. You first take the original, convert it to grayscale, then we convert to binarization. We remove the borders and pictures that we're not particularly interested for OMR purposes. Again, you also remove the lyrics. We separate the lyrics so we can do that with optical character recognition, right? And then we remove the staff. Musicians freak out because there's no staff line, they can't read it. But that's okay. Computer knows where they were. Then we can look for shapes or the musical notes. And we'll talk about how we recognize those later. So now we know things like a clef. Now, clef, you need to figure out what the pitches are, okay? So then we put back the staff line. And finally, we can tell what those pitches are, right? Knowing the clef plus where it is on the staff line. Then we can put everything back together. Then we can do the search, and we can find stuff. Now, Calvo's method, the layout analysis, can do all first 5 steps in one shot. It's amazing, right? Because each step may introduce errors, and they reoccur. Errors earlier in the process could make it even things later worse. So it was amazingly useful. So let me talk about just sort of general workflow of the SIMSA new notation workflow for the OMR. We're not going to go through all this, just sort of giving you how complicated these things are. So we're going to talk about this part. We're given the digitized, so we need to figure out what the layout of the document looks like, and we'll later talk about this symbol classification. Okay, so the problem is this. We have the original image, looks like this, and we want to be able to classify different things that are on the page, right? This is the notes, these are the text. The white is background. Humans are so good at figuring out foreground, background, we don't even think about it, but the white means it recognized that it was a background, okay? Now, so this is sort of figuring out the background. Binarization step usually does this. This is for the staff lines, right? It's doing pretty good. And this is for recognize where the text is. No, that things overlap, right? Text and notes overlap. And so in summary, what you want is you want to have the input, you want to separate the background, detect text, and find staff lines, and leftover will be the notes. Here's another example, right? Red is the text, blue is the staff line, black is the notes, and white is the background. Okay, so here's another view. So the original, what we want to be able to separate. And it took a while, before this Calvo's method, it took a while to do this. So how do we make this happen? So we need to teach the computer, for this convolutional neural net, what these things are, and we need to prepare labeled training samples. If there's any machine learning session this week, you'll probably hear a lot about training samples, and it has to be labeled, and these things are called ground truth. And these are usually created by human teachers. You have to label them or annotate them, okay? So just quick review on different types of machine learning. So basically there are three main categories: supervised learning, unsupervised learning, then reinforcement learning. Now, under supervised learning, we could have decision trees, right? You will not be tested on this. No, you can take support vector machines, neural networks, k-nearest neighbor, large language model, self-supervised, unsupervised learning involve clustering. Reinforcement learning is like robots and autonomous cars, and fine-tuning for large language models. So in order to create the ground truth for this Calvo's method, what we need to do is we need to label every single pixel of the image, right? So what we do is basically sorry, gotta go through this again. Okay. We have to go label one pixel in the center of this box, right? So we actually take the neighborhood, 50 by 50, but this 50 by 50 image or sub-image is labeled as what is in the one single pixel in the middle of that. So this is a text, this is the staff line, and this is the note. Sorry, the other way. This was the note, because it's from here, and this, I can't just tell from here. Staff line, and this was part of the text, right? Okay, here are some more examples. Sample of background. So we have to label the background too, but actually, everything else we didn't label. are the background, but see, these are the background. Again, we're only looking at the single pixel in the middle. Text, these are all text, okay? That's what we have to annotate. So we actually created a editor or front end called pixel.js by a few undergrads that we hire every summer, so that we can do this fairly easily, so we can block parts of the area, and this was called pixel.js. So here's a full page of annotated or ground truth of this page. To annotate one page of a manuscript containing over 30 million pixels took 24 hours. One page. 3 days of 8 hours. Poor research assistant who had to do this for. It's a boring job, right? But this is not going to scale. I'm too lazy. We can't have people doing this all the time. So what do we do? So we thought about teaching computers how to do these things. So pedagogy. What's pedagogy? Pedagogy is the art, science, and practice of teaching. Pedagogy, child, right? Greek, paidios, child, pedagogy. Andragogy means a teaching adult. So I came up with a new term called McGill, that we're teaching machines. Unfortunately, that was, I think it was in 2018, but year before, there's a guy named Mark Stefik Park, formerly Xerox Park, has posted something on the internet. So this word was used, so I can't claim it, but still, McGill, I'm sure you've never heard of it, but it's fitting for what I'm going to talk about. So McGill is the study of how to teach machines, okay, where we exploit the human skills to effectively optimize the performance of machines. It involves one-on-one teaching scenario, like in music lessons. It's exemplar-based. You show them examples, your student, the machine examples, the training data, and there's different teaching strategies, right? So that's pedagogy is about, or McGill is about. So how do you select the example to show or teach the machine, and in which order do you show the examples? I mean, if you ever taught young people, I'm sure you think about these things. So no different with machines.
If you can project a little bit at the back, I'm saying that sometimes people can't hear you as well. If you want to project a little bit, or we'll try the mic.
Okay, I'll try. So then we have feedback or evaluation method. Okay, so step in teaching machines and what's called the human in the loop. That concept is common. You'll hear about this. So human in the loop McGill. First, the teacher or a human selects small portion of an image. So we're now teaching how to do the manuscript annotation. The teacher annotates these sub-images, use these annotated sub-images as training data, ask the student or the machine to classify the image. We only give them a little bit and ask it to classify it using neural network. The teacher looks at the results and selects portion of the image that the students did poorly. Then go back to step 2 until the teacher is satisfied. Okay, so I'm going to illustrate this with what we did. So teaching session number 1. So this is the original manuscript. So we only take, rather than doing the whole thing, we just take parts of it and annotate that, right? Then you tell the machine, go. Yeah, the machine says, well, you didn't give me a lot, but I'll try. So here's the ground truth. That's what it should look like. And here's the original image, and this is what the teacher actually annotates, right? Okay, so given that, we're going to see what the results look like after the neural net has worked on it. It's actually not, it's not bad, but it's not great. because this is supposed to just show notes. But you see some letters here, you got all this stuff down here, you got other red stuff and things. So it did okay, but not great. So we're gonna give it more results. Here's some examples here. So this should be just notes. This should have been just notes. So we have some leftover from the text, big text, more text. No staff lines though, that's good. You learned that. So we don't have to teach that anymore, right? Do you understand? Because it can do it already, why waste time? This is actually lazy for teachers. Okay, here's another example. We'll see this later. User notes has a little blank space in it, which is not great. So, and the color bar at the bottom, which you need whenever you digitize. So here's a teaching session number 2. You give them a little more data, okay? Then we'll see what happens. Here's the ground truth. And just the result after this additional examples. And it's doing, see that red letter disappeared. This stuff is still down here. A little better. Let's see how well it did in detail. So remember, this was the original image. It's gone. It's a little bit left, but it's doing much better, right? So this was before. Okay. Inclinatum. So that's what these things are called, these rhombus, I guess, shape. So it's doing much better than what it used to look like. So this is only after second session, right? Color bars are not doing great. So we decided we're just going to crop that out, which is just no hope. Sometimes you have to give up. Here's an example. There's this thing called custos. Anybody know what this symbol is? There's no pitch associated with this. You don't sing this note. What this does, remember I said these manuscripts are huge? So it tells you what the next pitch on the next line is, right? Genius, right? But it missed that, right? There are a few other things that it's missing. That text. Again, this is supposed to be just notes, right? And there's text there, right? Sort of looks like notes. Okay, so teaching session number 3. So we add a few more things, right? This custos here, more text, this blue color text, and because it uses color too as a learning tool or things. So we added custos and more text, and these are the ground truth and result for notes. Much better. Got the custos. Here it's really hard. This really looks like part of a note, but that's okay. It's doing much better. Right? This is what it used to do. It was missing that custos, had all this stuff. So it's doing great. So we've been looking at just notes. Here's the results for text, just text. So it's doing quite well, right? There are a few things. Yeah, this little thing here, but it's doing quite well. It's basically now it's automated, right? It says extract text from this image. It's doing that, right? So always when you're doing machine learning, what's important is what it does with things that's never seen before, the test data. So this is with the new image. So we trained a little bit, and this is giving a brand new image page, and this is the notes. It's never seen it before, right? So it's pretty good, right? I think it's got most of the notes. Here are the staff lines. No, see that red line up here? Well, it's kind of hard, even for us. You didn't know, right? That's okay, we'll forgive it. There's a few things here. Yeah, you feel really like you're talking to a child or something. There's forgiveness involved. and here's the text. People say, well, it looks the same. Well, that's exactly the point, right? Right. So it's been good. So the strategic interactive teaching reduced the creation of training data from 24 hours just down to 6 hours. And this was just one time. As teachers get better, you don't know what needs to get taught. And so we're getting much, much better at doing this. Okay, so gives higher user-teacher satisfaction. All right. Okay, remember we talked about different types of learning. Now, we've been using convolution neural network. It's not lazy. It works really hard. It's called eager machine learning. As you saw, it takes a lot of preparation, training data, etc., and it takes a lot of time to compute. So which one of these are lazy? I'm supposed to talk about lazy learning, right? Some of you may know already. There's only actually one out of these. It's called the k-nearest neighbor. It's an amazing machine learning algorithm. It's also the most simplest. And I'll talk about that for the next few minutes. So lazy, it's also known as exemplar-based learning. The exemplar-based learning model is based on the idea that objects are categorized by their similarity to one or more stored examples. So we store examples and we compare. There's much evidence from psychological studies to support exemplar-based categorization by humans. This model differs both from rule-based or prototype-based models, such as neural nets, of concept formation, in that it assumes no abstraction or generalization of concepts. We normally think we abstract things, we generalize things, that's how we go about in the world. In fact, that may not be quite true. We do that, obviously, but in a lot of tasks, we just learn by examples. This model can be implemented using k-nearest neighbor classifier and is further enhanced by application of genetic algorithm. That part is really cool, but I'm not going to talk about the GA today. Applications of lazy learning models. So I was quite early using k-nearest neighbor because that was the only machine learning algorithm that I understood. All the other ones I couldn't get it. So in the '89, there's been other interesting application of k-nearest neighbor, things like vehicle identification, pronunciation, cloud identification. Imagine teaching machines how to categorize different cloud formation, right? Respiratory sound classification. This one actually saves lives. Most stuff we do don't save lives, usually. Wine analysis, right? So robot scene analysis. Tomato classification, like rotten or not rotten. So even as late as 2 years ago, people are still using k-nearest neighbor. So how do you implement this? The lazy learning model can be implemented by the k-nearest neighbor classifier, a classification scheme to determine the class of a given sample by its feature vector. Feature vector simply means a point in feature space, okay? 2D, 3D, 60D. The class represented by the majority of the k-nearest neighbor, replace k with 1, 3, 5, okay? Is then assigned to the unclassified samples. So classification problem, you don't know what it is, and you want to figure it out, right? So you just put it in this feature space, and bang, you know what it is. Look for the people close to you, things that are close to you. Besides its simplicity and intuitive appeal, the classifiers can be easily modified by continually adding new samples that it encounters into the database to become an incremental learning system. Again, we're getting it to learn slowly but surely. Okay, so there's always been criticism because you have to store all the examples. It takes a lot of memory, and it turns out you have to calculate the distance to all its neighbors. So it takes a little time, but in the days of large language models, this is nothing for the memory or time. This is a quote from 1993. The nearest neighbor algorithm is one of the simplest learning methods known, and yet no other algorithms has been shown to outperform it consistently. It is 1993. The KNN classifier is the simplest of all machine learning classifiers. It is based on the principle that the things that are similar are close by. Okay. A few years later, many sophisticated classification algorithms have been proposed. 1990s were huge machine learning. People just using it crazy, like today with large language models. According to our experiments on popular data sets, KNN with properly tuned parameters performs on average the best. It may not always be the best, but it's pretty good actually, is what they're saying. It determines the class of a given sample by its feature vector, distances between feature vectors, points in space, of an unclassified sample, and previous classified samples are calculated. The class represented by the majority of k nearest neighbor is then assigned to the unclassified sample. Are we okay with time? Yeah. Okay, I'm going to give you an example. How are you going to tell the difference between basketball players and sumo wrestlers? Okay, how would you do that? Okay, so we use a KNN classifier, and all we do is store the known people. So this is the weight, right? This is 2D. This is the weight, and this is the height, right? So it's pretty obvious, right? Sumo players are shorter and heavier. Basketball players are skinny and lighter. That's all you do. You just store them. No pre-training, no nothing. So let's just assume that you're all Martians and you didn't know who Michael Jordan was. And you want to figure out whether Michael Jordan is a sumo wrestler or a basketball player. So you don't know. So this is the unclassified sample. So all you do is place Michael in this space. Here it comes. It's possible. He's right there. That's his height, whatever, 200 centimeters and about 90 kilos. You just place his data, and you just look for his neighbor. And the closest neighbor is the basketball player, so he must be a basketball player. That's all it is. That's all KNN does. You can look for 5 neighbors, but that's it. It can't get much simpler, but it's quite effective, and that's how we identify these music notations, right? And actually, you don't have to give a lot of example for it to learn. You don't have a lot of classes. You give him one treble clef, right? You say, okay, this is a treble clef, and you give him something else. It's going to say, let's say you're going to give a bass clef, right, a lower. And it's going to say, oh, it's a treble clef, because the only thing I know is treble clef. And then you say, well, no, this one is called the bass clef. Next time you show him another bass clef, it'll get it. It took 2 training samples to identify these 2 classes, right? Because they look different. They don't look similar. And actually, music is good because music's notation was designed so that the musician can read them very quickly without errors. So this works particularly well. And that's how we did the lazy learning without doing lots of training samples. Okay, switch gears. I'm going to talk about this new project called Link Music. It's integrating music databases, right? There are hundreds of music databases, little ones, mostly little ones. And yes, there are information on the internet, but it's really it's really time-consuming to know where these databases are, then look for them, and get used to their user interface. So it's a pain, and we wanted to put all these music databases together. So goals of Link Music project, make music information accessible to more people in the world, be able to search across various music data from one website, and make musical queries available in languages other than English. So funding, again, thanks to many people in this room who reviewed these grants. We have co-investigators including UDM. UDM is Université de Montréal, that's how we say it in Montreal, UDM, and Dalhousie, etc. We have many collaborators across the world, partners again, and we have many summer students. Okay, so here are the 15 databases that in the application we say we're going to integrate. Okay, some of these you may know. So we have some classical music, early music, prints. This is printed books, chants. This is sort of what we might call the world music, jazz, many other things, motet, sessions. The session is like actually Irish music sessions. Okay, so what are the challenges in integrating databases in general? So schema, which is how data is structured, don't match, right? So different databases could have different headings. One may say songs, which may be the same or different from tracks. Semantic differences, artist, performer, right? Apple Music is particularly bad with this, as you may know, especially for classical music. Genre difference. What is folk music? Huh? Here in China, right? Integration complexities. Different database has different way to encode things. One may say Ludwig van Beethoven, they might say Beethoven, Ludwig van. I'd be the same people. This one's the obvious because we know these, right? Okay, so let me briefly talk about different types of databases because we want to put all these things together, these databases together. So there are data sets, there are databases, data warehouse, which collects lots of databases, and there's sort of a new concept called data lake. Okay, so here's some examples. You're probably most familiar with data sets like spreadsheets, JSON, or relational databases here. There are other bigger things. Now, we chose to use data lake because it's totally unstructured. We don't have to structure. We don't have to do any work. We're lazy, right? So we can put anything. We just dump them into data lakes. But it is used for things like business intelligence and machine learning. We worry about how to organize that data in the data lake later when we need it, right? Do you ever wonder how Amazon store their inventory in their fulfillment centers? It's called chaotic storage system. It's crazy. I don't know if you can see. I have a bigger one. Look, here's a Band-Aid. Here's a hairspray, headache medicine, Oreo, Echo Dot. They just put whatever comes into whatever empty space there are. And that's recorded. And when order comes in, the computer figures out what is the shortest path to go pick up these things for humans or either the robots to pick these things up. They don't care how things are stored. I mean, how are organized. Doesn't matter. We'll do it when we need it, right? I mean, this is super optimized, right? Okay, back to our main topic, lazy searching. So when you want to search across different databases or data sets, there are basically two kinds of searches. One's called harvested and one's called federated. Harvesting search is what Google does, right? It collects all HTML and then it's indexed so you can find them, right? Federated search, on the other hand, you don't do it until it's asked. So it's on-demand searching, things like airlines and the hotel, your kayaks, Expedia, all that. But this needs pre-agreement that they're all going to have sort of the same format of information when they go and ask each hotels or each airline for their information. Takes organization. Too much bureaucracy, we don't like that. So lazy searching, so it's basically we harvest, but we don't index. We just collect and dump them into data lakes. It's called the schema on read. That is when we're trying to read off the database, right? Data lakes store raw data without enforcing a schema up front. The structure is applied only when the data is queried. Again, we postpone what we need until later. So our process of doing this linked music at this point is we convert various databases into flat files like CBS or JSON LD. LD stands for linked data. And we reconcile or convert schema, properties, and entities in the database, things like name, place, title, to Wikidata URIs using OpenRefine. I'm sure you'll learn about OpenRefine if you don't already know it. It's an amazing tool. Then we store the results in OpenLink Virtuoso graph database in RDF or linked data format. Then when we need to do the query, we use what's called Sparkle. So this is what sort of basic process looks like. We start with the databases, we put it into simple format, we reconcile using Wikidata, using OpenRefine, dump it into Open Data Lake, we call it a graph database. And then we can search all types of music information. Then if we need more data, so we're basically only concerned with the metadata, right? And if we need like images or sound, we go to get it from the original site. Okay, I got 10 slides, 30 seconds each. Okay, Sparkle stands for Sparkle. Again, we're not going to get into this. And we use natural language query to Sparkle conversion. This is really cool. I won't talk about it. We use ChatGPT to do the conversion using prompt engineering. But that's another talk. No training is necessary. Query can be done in any major language. This is really cool, right? It's Sparkle, but you can ask it in any language because ChatGPT is smart enough to translate. Anyways, benefits of our system. By converting a database to an RDF graph database, reconciling with Wikidata, no schema alignment necessary, no work. Because we use ChatGPT, we can make questions in many different natural languages. We can even make queries that were not possible with the original web interface, because we have the original data. Furthermore, because we reconciled with Wikidata, we can query with concepts that were not defined in the original databases, like find female composers. Often genders are not stored in these databases, but in Wikidata, many are, so we can do that. Because RDF can be stored as text files, we can easily archive them for long-term preservation. This is a new idea, and we're ongoing research. We improve NLQ to Sparkle process across various databases, use LLMs to generate web pages. So it's getting really smart, right? ChatGPT will create a web page on the fly, and there's another service where you can serve it online. So whatever data you got, you can make it so it looks nice on the web page, and you can sort and filter all that stuff on the fly without knowing how to program. As I said, long-term accessibility of databases, continue to update Wikidata for musical information. Our postdocs is improving concept about saints and feasts. It's important, especially in the medieval ages. So big research question, how can we keep Wikidata accurate and up to date? So we're putting all our eggs in one basket called Wikidata. It's messy. but we're going to try to improve it. So remember Wikipedia was really messy and unreliable at the beginning? Maybe if we work at it, maybe we can make it something very useful because it's really cool. Okay. What we covered today, we talked about lazy learning, Simpson project, using of K-nurse neighbor classifier and optical music recognition, metagogy, human in the loop teaching, lazy pedagogy, creating ground truth for document analysis using CNN, lazy storage and lazy searching, linked music project, where we do music data integration. Final thoughts. The virtue of patience in humanities research. Just as literary analysis or historical inquiry benefit from slow, deliberate reflection, lazy machines thrive in environments where quick answers aren't always required. This contrasts sharply with the real-time demands of many AI applications today. Dump and query paradigm, a practical design for integrating diverse databases by postponing schema alignment and metadata harmonization. Lazy systems avoid premature optimization. Future-proofing, by avoiding early schema alignment, our system always stays flexible. Laziness as respect for uncertainty. Humanities research often deals with ambiguity. Our system embraces this by not forcing premature decisions. Human in the loop as a strength. We collaborate with machines. Laziness as deferring to human expertise. Error corrections and incremental learning. Interactive training improves systems without massive training. Serendipity in exploration. A lazy graph database might reveal unexpected connections, valuable in humanities research. Resilience to obsolescence. Heavy processing often locks data into outdated formats. Our approach keeps options open because we're lazy. There are over 100 people that worked on this project or projects. This is our current summer. They're probably working right now in our lab. And all this was because of these people and also to the funders. Thank you very much.